Everyone, I'm glad to be here. I'm going to talk today mainly about active nearest neighbors in metric spaces. I'm also going to talk about another thing in the end. This talk is about doing active learning, and the sort of kind of goal for me is to try to do active learning under minimal assumptions. So we don't want to sort of assume something, then go try run it, then it doesn't work because our assumptions were wrong, but it's too late because we already sort of spent our budget, for instance. So this is sort of the focus. I'm going to talk mostly about active nearest neighbor in metric spaces with, this is joint work with Arya Kantorovich and Ruth Urner. And in the end, I will talk a little bit about active linear regression. This is work with Remy Munoz. Okay, so just to remind us all what we mean when we say active learning, it's a specific type of interactive learning, a very maybe structured type. So first, let's remind ourselves what is passive learning. In passive learning, I'm talking about supervised passive learning. I have some sample of examples. I have, for each example, the corresponding label. This is my training set. I feed it to my computer, say. The computer learns a model. The model is kept somewhere. And then when there's a new example, say this 3 here, then using the model, the model will be used to sort of output the right label. Okay, so this is standard passive learning. And the problem that we're dealing with in active learning is we don't want to actually require all of these labels here. In many cases, this can be very expensive. In many cases, examples are actually easy to come by, so it's easy to find a lot of images, etc. But labels could be much more expensive, so we want to save that. So this is the problem that we're dealing with here. So in active learning, the idea is, okay, instead of just asking for all of the labels in advance, let's just have some mechanism, some oracle that will be able to give us labels. It could be a person in case of digits. It could be maybe an experiment if we're in a biology setting and we need to do experiments to get labels. So this person in this example, so the model gets a set of samples, but without the labels, and then it can sort of choose some example from here, ask the person or the oracle, what is the label of this example, get the label back, etc. And then in the end, we do the classification the same as before, based on the model that we got from this learning process. So the goal is mainly, okay, we want to select smartly which examples to label so that we can save dollars or whatever other resources that we pay for getting labels. That's the main goal in active learning. So one topic in which I think it's safe to say that we know quite a lot today about active learning is in the case of parametric learning. So in parametric learning, we assume that there is some fixed limited capacity concept class that we set in advance. Say it could be linear predictors in some space, or it could be decision trees, or it could be anything else. And we try to approach the error of the best concept in this class. So this is parametric learning, and I will talk about classification. So I'm assuming there is some small discrete set of possible labels, say the numbers, or sometimes even just binary classifications, the 2 labels. So for this type of model where we have active parametric labeling for classification, I think we know quite a lot about it. There has been a lot of work during recent years, much of it by people in this room. And we know a lot about realizable setting, about the agnostic setting. We have disagreement-based algorithms. We have margin-based algorithms. We have near-optimal strategies. In some cases, we have lower bounds. We know a lot. And this is a very interesting and good progress. But then it doesn't solve all our problems, because this is just for the parametric case and just for classification. So today I'm going to talk about 2 problems that do not fall into this setting. Mostly I will talk about the non-parametric setting, and then I will talk about regression, which is also not a classification problem because the labels are not discrete. So, okay, let's talk about non-parametric learning. What do I mean by non-parametric learning? I just mean that we don't assume any specific concept class. In general, in non-parametric learning, you usually expect that if your training set is larger, the complexity of your concept class is, or your concept is larger, or your model. And in this model, we just try to approach the base error. We don't sort of compare ourselves to a specific concept class. We just try to approach the best possible error for a classification. Specifically, I'm going to talk about approaches that use nearest neighbor classification. So I'm assuming some metric space, and then in this space, I'm looking at a method that does the following. So first it looks at the sample. Using the sample, it creates some database. So the database will be just a set of labeled examples. And then based on this database, it will classify new examples using the nearest neighbor rule. So any new example that comes in, I will find which is the example closest to it in my database, and I will give it the same label. Okay, so very sort of intuitive way of doing things. So I will look at this sort of setting. And what I'm going to do in this work is the following. I'm going to present a nearest neighbor active learner that has a competitive accuracy to a passive learner, which I will describe, that is designed to have this sort of property, to use a nearest neighbor rule. And the goal of the active learner is to try to use less labels. Now, it's not always possible to use less labels, but if it's possible, we would like to be able to do that. And we don't want to make any assumptions on the distribution, so the algorithm should just run. You don't need to tell it anything before it starts running. And we want, of course, finite sample guarantees, as we like to have in this field. A central challenge, which I will get to after a few other discussions, is active model selection. So what happens here, unlike the fixed concept class case, is that we have to somehow decide on the complexity of our model. And it's a challenge in active learning, because usually to do that, what you do is you just try a lot of different models. In passive learning, that's not too bad. But in active learning, every time you try a different model, you might pay a lot of labels. And you don't want to do that for all of the different models, just to choose one model in the end. So it's a serious challenge. There is some related work on non-parametric active learning. But again, I think in general, it's much maybe sparser, less we have less of a general picture of what is going on in that space. Some works are listed on this slide. We have cluster-based active learning. We have minimax rates under decision boundary regularity. We have some graph-based active learning in this setting. In general, these are very interesting works. What I'm trying to do, which is different, is to sort of try to get rid of all the assumptions, sort of not try to assume anything in advance. And also, it's a good time to mention that this afternoon we have Steve talking about his nearest neighbor active learning work, which is also very interesting.
I have a slide.
Sorry?
Just one slide. Yeah.
Oh, okay. Okay, so let's be a bit more formal. We're assuming some metric space X with some metric rho. There's a finite set of labels in this case, so in the multi-class setting. And we assume some unknown distribution over the examples and the label, the joint distribution. And we have some examples and labels drawn from the distribution. This is our input. This is our training set, basically. And the output, we want the output to be just a classifier that gets examples and outputs labels. The goal here is to just get a low error. So we want the probability of making a mistake on a new random pair to be small using our learned classifier. Okay. So this is just a non-parametric learning in general for our model. When I'm going to compare passive learning to active learning, so let's just define that. So passive learning, I get a sample S. It's a random IID sample out of my distribution of size M. And I output a classifier. In the active learning case, I'm going to talk about pool-based active learning. So I'm getting a pool. The pool is just the examples without the labels. And I can just interactively request some of the labels. I can ask for, give me the label of example 3. I will get the label. Then I can ask for another label, etc. And I can do this interactively. And again, I will output a classifier. Okay, so the only difference is the way that I'm getting the labels. I don't pay for them all in advance. I can choose which of them I want to pay for. So this is active learning and passive learning. Now let's talk a little bit about nearest neighbor rules. I'm going to talk about one nearest neighbor. So it's a very simple approach. You fix some labeled set. I'm going to say what it is in a moment. So some set of examples with labels. And this is basically our model. And then every new example that we get, we will just find the example that's closest to it in this set L and label it the same. So if I'm drawing this, basically each color here is a label. Basically every point induces the region around it which will have the same color. And if I get a new point, I will just check which is in which Voronoi cell it lies, and this is what determines my label. So this is a one nearest neighbor rule. In the passive learning case, there are some approaches that are worth talking about. So in general, what is the general form? If we're in a passive setting, we want to build a one nearest neighbor model. What we basically need to do is we just take the training sample, which we know. We need to use it to set some set of labeled examples. And then this set will be used as our nearest neighbor database. Now, the classical algorithm that we probably all know about is one nearest neighbor, which just says, okay, take just the whole training set. This is your database. Okay, this is a very simple, very intuitive approach. So in this case, L equals just the set. What I'm going to talk about today is a more sophisticated algorithm that has some advantages. It's a compression-based algorithm, a passive learning algorithm. In this algorithm, the database that I'm going to use is a subset of the training set. So I'm not going to choose all of the training set, not necessarily. I might choose a subset. This is work by Gottlieb, Kontorovich, Krauthammer, and Weiss. And what they do is they propose this algorithm. The advantages of this algorithm, okay, so first of all, by taking a subset, of course, first of all, it could be better, right? I mean, we could just be able to compress our data set. We don't have to save all the data set in our model. That's, of course, useful computationally. Also, what we get is this is a way to regularize basically our choice of data set. So instead of just choosing the entire set, we can choose a smaller set. And by this way, we can get the generalization error to be actually smaller because we don't have this basically fixed, uncontrolled set that we are using.
It's not that the error is smaller, it's the generalization error is smaller.
The error on the distribution.
The error on the distribution can evolve because you're playing with the approximation error.
Now, what I mean is I will select the set L. I will talk about it a little bit more in a moment. But I will select the set L such that my sort of bound for the error on the distribution is small. Okay, that's what I'm trying to do, right? And for this type of algorithm, we have a finite sample and data-dependent error guarantees. So based on the data set that we saw and the L that we chose, we can have guarantees. And the regularization that comes from being able to choose the data set gives us more control over the final error. So we're going to look at this passive learning algorithm. And so this is sort of our benchmark. We want to try to do something similar to that, but we want to try to do it using active learning and less labels. Okay. So I'll first introduce our main result, and then I will go back to how we do that. So we propose this new algorithm, MARMANN, which is a one nearest neighbor active learner. And the guarantee is with respect to the guarantee of this passive learner. So the passive learner basically guarantees that the error that it gets is smaller than some generalization bound, which depends on the sample, the input sample. This is an empirical bound, which is based on compression bounds. What we guarantee instead is that we have an active learner, and it obtains an error bound which is up to a constant, the same as the error bound of the passive learner. So we pay by some constant factor on the error. So this is the competitiveness with the accuracy. But then the advantage is that we will require less labels. So basically the number of labels that we require is about log 1 over delta, 1 over g plus mg, where g is basically our guarantee for the error of the output classifier. Okay? So what happens here is if g is very large or very small, then we don't gain much. We're just basically going to use the whole pool of examples and ask for all the labels. But we do gain if g is somewhere in the middle. Okay? So the best case would be when g is about 1 over square root of m. So this is the error that we guarantee. And in this case, we will use about square root m labels instead of m, which is the size of the entire pool. Okay? So this is type of a luckiness result. I mean, if we are in a setting where g is very large or very small, we're not going to get improvement. But if we can, we will. Okay, and this is sort of, yeah.
So the previous passive, the compression-based result,
Right.
If it started with n points, what size would it shrink that to?
So it depends on what you can do. Maybe we'll defer it in a moment, and you will be easier to see that.
Sivan?
Yes.
So just to be clear, when you do the subset based on a compression bound, you have to do that after you've looked at the labels of everything. So you can't just naively say that.
Right. So I will kind of get into more detail in a moment, and we will see what the passive learner does. Yes.
And the constant C there, is that a universal constant?
It's a universal constant.
Okay.
Yes.
So no distribution.
No. Yeah.
Is G, do we get to choose G?
No. So G is kind of whatever the active learner gets is manages to do.
So isn't this kind of a niceness assumption of the data to get a useful G? Because if the data, you said I'm making no assumption of the data. But it may be that your G will be very bad and this will be meaningless.
Right. So the thing is, of course, to get an improvement in the number of labels, I need G to be good, but I guarantee accuracy no matter what. So the point is,
in terms of some intuitive property of the data, what will make G useful?
I think it will be easier to see once I sort of show some of the algorithm, okay? And it will be clear where these two terms come from, okay? So let's talk about what is the algorithm, and I will start with explaining the passive algorithm for a moment, and then it will be easier to also explain the active algorithm. So I will first talk about the passive algorithm, and then I will explain the different parts of the active algorithm. So, the passive algorithm works as follows. First, it looks at the data, and it wants to find basically a separated set. So what's a separated set? Let's say we have a scale gamma. A gamma separated set is a set where a sample is a set where two examples, if they are gamma near, then they don't have different labels. Okay, so every two examples that are not the same label are gamma far. That's a gamma separated sample. Of course, the original sample should not be a gamma separated sample, but then what the passive algorithm does, it does the following. First, it removes all the points that interfere with this gamma separation. So basically, you can think of it as some sort of noise reduction, removing noise from the sample. And then it will define a gamma half net on the rest of the points. And this half gamma net is a compression set that can be used as a nearest neighbor database. Okay? So
Gamma a margin?
I'm sorry?
Is the gamma a margin, basically?
You can think of it as a margin, yes.
So you can map everything like to 1 over gamma square dimensions. Right? Well, this is the usual gamma.
Well, if you after you remove the noise, you might be able to do that, yeah.
Just use the Lindström after you remove the noise.
But this is in the general metric space.
So Johnson's lineage also it's not Euclidean. This is
No, it's a general metric space.
okay.
I'm not sure what Johnson-Lingstrauss knows how to do for general metric spaces. So it's a general metric space. So this is basically what you can do if you decide on a scale, your scale is gamma, then you can say, okay, here is my gamma compression. I will remove the things that make noise in this gamma scale, and then I will just select this half gamma net on the rest of the data, okay? But this is just after you know gamma, okay? So I sort of told you I have some scale gamma and use that scale. In reality, we don't know gamma. Again, it's not a parameter of the algorithm. What happens is, we are going to find gamma, okay? Yes?
So when you're trying to remove these gamma separated points, you have some choices. Does it matter?
Yes, there are choices. What you want to do is you want to remove the smallest number of such points. This is actually a special case of a vertex cover problem.
Okay.
So it's easy to do if there are two labels. If there are more than two labels, you can do a two approximation.
Sorry, you want to remove the minimum or you want to keep the minimum?
No, I want to remove the minimal number of points, and I will show that in a minute because it will come up in our bounds.
So you stay with a large set?
Yeah, I want to stay with the largest set possible. I want basically think of it intuitively. If I have to remove a small number of points, this is like saying there was little noise in my data, which is of course a good thing. Little noise is a good thing. So a small number of points, little noise. So here exactly this is related to your question. So let's denote by nu of gamma the smallest fraction of points that needs to be removed to get a gamma separation. This is again related to the vertex cover problem on a graph defined on this sample. And what we have is a compression-based upper bound for gamma. So given a fixed gamma scale, the generalization error is going to depend on nu of gamma, the fraction of points that I had to remove, plus these terms that depend on n gamma, which is the size of the gamma net, and the size of the sample, and log 1 over delta, which is our confidence. Okay? So this is the compression bound. It's not very easy to show. It's shown again in this previous work on the passive learner. And the idea is that, okay, we have this bound for every scale gamma. Let's just choose the best scale. We will try all the different scales. We will choose the best one, the one that minimizes this generalization bound. Okay? So this is what the passive algorithm does. Now we want to compete with that passive algorithm. Okay? So our goal is to get similar error guarantees, but we want to do it actively and we want to save labels. We don't want to use very many labels. So what we need to do is we first need to select gamma using few labels. This is our model selection problem. And second, we need to, given gamma, set the database L also using few labels. Okay? Now this is not trivial because the algorithm that I just showed you does not take this into account. It doesn't care. It can look at all the labels. It wasn't designed to use few labels. Okay? So even though the algorithm first selects gamma and then sets the L given gamma, I'm going to explain it the other way around because the second one is easier. Okay, let's just assume we have gamma and we just want to set L. Okay? So if we have gamma, if we wanted to do what the algorithm I just told you does, we would have to sort of find the minimal number of points to remove from the sample to make it gamma separable. But this is a hard problem in terms of doing this with a small number of labels. It's also computationally hard if you have more than 2 labels and you can only get a 2 approximation. So instead we do something else. What we do is the following. We start with setting a gamma net. So we define a gamma net L tilde gamma, which is a half gamma net on the original sample without removing any noise. After we did that, we take each point in the gamma net and we randomly sample labels from the Voronoi cell around it and check what is the majority label. And what we do then is we set the label of each of these points in the gamma net to the label of the majority around it, or the estimated majority around it. Okay? So what this means is, unlike the original algorithm, we don't just take a subset of the labeled examples. We take a subset of the examples, but we put our own labels on them. Okay? So it's a bit different. It's not the totally standard compression scheme, but it's not also very far from it. So you need sort of a compression with side information because you want to be able to change the label. And then you can show basically, even with side information, it's almost the same. So generalization error that we get is almost the same. Yes?
So when the step that you're not talking about, the search for gamma, you probably start...
No, here I'm assuming you know gamma.
Right.
Yeah.
You probably start with a large gamma and you then...
Not exactly. I will show you later.
Which somehow seems like it turns into something very similar to the Dasgupta-Shu hierarchical algorithm.
So I will show that we don't actually do what you're saying. Yeah.
Majority in the sets.
So it's actually not what we're going to do. I will talk about it when we talk about active model selection. And the reason is because this is the way that we need to do to save labels. Okay, so, but let's just for a moment stay with the fixed gamma. So for a fixed gamma, we have a generalization bound that can be given. And we can show that this gamma net that I've defined gets the error, which is a constant times the nu of gamma, the same nu that we had before in the passive algorithm. So this is a very good approximation. And basically what happens here is once you know gamma, the number of labels that you need is going to be proportional to the size of the gamma net. Now this may look like a lot, and it could be a lot, but it's also the only thing that you can do. Because basically there are lower bounds. You can show that in general you do need this number of labels to be able to get an error which is competitive with the error of the original scale. Yeah.
Sorry, what do you mean with random label sampling? So the algorithm just randomly samples labels?
So it randomly samples labels in each Voronoi cell of a gamma net. Yeah, it's almost randomly. Yeah. Okay, so the point here is, okay, so we need an n of gamma points in order to, O of n gamma labels in order to get this right. And this is a lower bound. So where is our gain? Our gain is if gamma is large. if we happen to find that a large gamma is good enough for our problem, then n gamma is going to be small. And if n gamma is going to be small, then we're happy because we used few labels. Okay, this is one way where you're asking what type of problem will allow me to use less labels. So this is one thing that should be happening is I need to be able to use a large gamma. Okay.
Gamma should be uniform throughout your space.
So in this algorithm, it is assumed to be uniform, yes. Although, of course, it probably can be improved to not be uniform. So this is a luckiness idea, and that is the entire, I think, idea of the approach is I don't assume that the problem is easy, but if it's easy, I'm going to be able to use less labels. Yes?
Gamma can be tiny and gamma can be small, right?
Gamma can be tiny. Well, it depends on the doubling dimension, essentially. But for a fixed problem, of course, if you increase gamma, your n gamma is smaller, right? I mean, it's
Yeah, absolutely. It could be tiny for tiny gamma, right? So you need they're almost touching each other, the examples, but you can take points very far from them to get the boundary. Just think of a hyperplane with 2 points. You can define the hyperplane as a Voronoi diagram, but if you want to separate the labels, gamma could be as tiny as you like.
okay. I'm not sure I follow your example exactly, but in general, the idea is just n gamma is the size of the gamma net that's needed to cover the space. So the space of samples. So obviously, if you use a smaller gamma, then you need more points in your cover. I mean,
But you can support a hyperplane with 2 points, right?
but it's not a hyperplane.
No, but suppose you did get a hyperplane.
Okay, so if you only have 2 points, your gamma is very large because the distance between them.
On the hyperplane on both sides, so your gamma is tiny really, because your gamma is.
Okay, what you're saying is it could be that there is poor separation, but there exists a small set which separates. That is true, but you will not find this set if you just use it like a worst-case gamma net. Okay, I cannot guarantee that you will actually find this set. It could exist, but you will not necessarily find it, because you just take in any gamma net, not the best gamma net for this problem. Okay, so the point is here, if we can find a good gamma which is large, then we're happy we have few labels. Now, how do we select the scale of gamma? So here's what we do. So again, our challenge is active model selection. We need to find gamma, but we want to use few labels, so we don't want to just try all of the different gammas and do the entire thing for all of them. And basically what we want is the number of labels that we use during this model selection algorithm should only depend on the selected gamma. Why? Because the selected gamma is basically what I'm going to guarantee in the end. So it's okay to depend on that. I mean, if I'm getting you a good gamma, that's okay that I'm using a lot of labels for that good gamma. But I don't want to use a lot of labels for something that I'm not even going to use later. Okay? So that's sort of our challenge. There is some previous work, interesting previous work on active model selection in the parametric setting with Nina Balkan, Steve Haneke, and Jennifer Wortman, but it's not suitable for what we need. So we're proposing another approach, and our approach is basically some type of a binary search. I'm going to call it binary search star because it's sort of not exactly binary search, but it's sort of a little bit intuitively it's similar. So how do we do that? So here's the idea. So we have this bound that we're trying to minimize over gamma. So the bound is composed of 2 parts, or 3 parts, but it is based on 2 properties. One is nu of gamma, and the other is the size of the gamma net. Now, we can rewrite this bound a little bit so that we can see that it's basically composed of two sizes, 2 quantities. One is, again, nu of gamma, which is sample dependent, and the other is something that I call phi of gamma, which we can basically calculate just if we know the size of the gamma net and the size of the sample. We don't need any labels for it. Okay, so phi of gamma is something that we know. Nu of gamma is something that we don't know in advance. Okay? So the nice thing that happens is the following. As you increase gamma, nu of gamma is monotonic increasing or non-decreasing at least. And as you increase gamma, phi of gamma, which is our penalty for the size of the gamma net, decreases. Okay, so we have two different quantities. One is increasing and one is decreasing, and we're looking to minimize the sum of them. Okay, so what we do instead is we're using sort of a binary search, as I said, binary search star, to look for a gamma where they are both about equal. It doesn't necessarily exist. So there are some details that you need to take care of, but let's just say for the explanation that they do exist, then you should just find the place where they are both the same. Okay, if they're both the same, then you have a small factor approximation to the minimal bound that you're trying to get. So based on binary search, you can basically say if this one is much larger than this one, I should go right. If this one is much larger, I should go left. Okay, this is the idea. But it's still not solving the problem because we don't know nu of gamma. Okay? Nu of gamma, as I said, is something that's hard to estimate. It's hard to find in the sample. So what we do instead is we look at the sample error. So the sample error is actually a lower bound to nu of gamma. And the sample error of a specific gamma net that we chose. And we can show that. And this means that now we have this epsilon of gamma, which the sample error for a specific gamma scale. It's not monotonic. It's not necessarily monotonic. But it is upper bounded by a monotonic nu of gamma. Okay? Using these observations, we can sort of fix binary search stars so that it still finds a good scale, even though it uses something which is not monotonic, based on this upper bound. Okay, so I'm not going to go into all the details. You have to be very, very careful. But if you do it carefully, then you can find a good gamma scale. Now, how many different gammas have you looked at? Just logarithmic in the number in the total number of scales. Okay. Okay, there is still one thing missing, which is how do you estimate this error, this sample error at gamma? And this is also non-trivial because, again, I'm not actually going to build the entire gamma net for each scale. I don't want to do that. This will just cost me too many labels. So what we are doing instead is, and I think I will really just mention this and not go into all the details. What we're doing instead is we're estimating this sample error only up to some accuracy. And it turns out that estimating the sample error up to a specific accuracy suffices for us to decide whether we should go right or left in the binary search. And this accuracy, we set it so that we never pay more than what we're actually going to get in the end. Okay, so if G, as I said, is our final guarantee for the error, then the number of labels that I'm going to use to estimate this sample error is going to be the minimum between the one over the error in this gamma and 1 over my penalty term for this gamma, which means that I'm not going to pay more than 1 over G. Okay? So again, what this means is I'm doing model selection. I don't know which is the right scale, but I can make sure that I never waste more labels than what I am willing to waste for the true scale, which I don't know. Okay? So this is a bit of a delicate thing that needs to be done, but it can be done. And in this way, we guarantee that even though we look at a lot of different scales, and even though the right scale might not be the one that we're looking at right now, we are never going to spend too many labels on checking this specific scale. So I think I'm going to skip the explanation of how exactly we do that. I will just say in general that this can be done using a general solution to a problem of estimating the expectation of a Bernoulli variable using sort of automatic stopping mechanism. So we need to basically know when to stop. When we estimate the expectation of a Bernoulli variable, we can draw random samples of this Bernoulli variable, and we don't want to draw too many, so we have to know when to stop when we have the desired accuracy and no more. And this can be done using empirical Bernstein bounds. So I think I will not go into all of these details now. But this is what we do to be able to do the model selection. Yes?
So first you're finding the right gamma, and then you spend all your time on
No, so to find the right gamma, I need to estimate the sample error at every point that I'm checking.
Right gamma, then do you invest a lot more in that one?
Right, so when I find the right gamma, this is only then I will actually spend this n gamma samples to actually get the entire model. So to do the estimate, I'm not actually calculating the entire model.
Reuse examples somehow that you've gotten between them, or they have to be all? I mean,
So probably we can reuse them, but we haven't done the analysis in this way.
because the gamma nets at different sizes are very different. Is that the problem?
Yeah, so the way that we defined it right now, you just have an arbitrary gamma net for every size. But probably you can build something that's hierarchical so that you don't have to resample, and it will probably save some labels, yes. I'm not sure it will change the order of everything, but it probably will save on the constants. Yep. Okay, so to show the entire algorithm, like in a sketch of the algorithm, is the following. So first we do the binary search star, which allows us to select a value for gamma. To do that, we estimate the error gamma of this gamma, so sample error of this gamma, up to some accuracy threshold, which allows us to not spend too many labels. Using this procedure, we can find a gamma star, which is a correct scale in the sense that it is a scale that will get us up to a constant away from the best accuracy that one can achieve. And this entire process of the model selection costs us about 1/g labels. So Shai, respect to your question, when g is small, this means that the error of the good model is small. And this means that we need more samples to differentiate it from another model which is almost as good. So we are paying 1/g for the model selection part. So here we pay more if the error is smaller. Okay. Now, the second part is, okay, I found a good gamma using this model selection process. Now, all I have to do is just get this specific gamma, calculate the gamma net that I defined before, calculate the majority vote for every point in the gamma net, which will cost me O of n of gamma star labels. And this is basically the model that I will output. This is the database, the nearest neighbor database that I will output. So here, repeating again the main result, we see that the number of labels that we need is really just the sum of these two terms. G star is the best error that you could get if you actually checked all of the scales to the entire accuracy that you can get with the entire sample. So basically, this is what G star is basically what the passive learner would get.
How does G star quantify over selecting the gamma net? Because given a gamma, there is more than one gamma net.
That's true. So for this algorithm, what we assume is you have some procedure for finding a gamma net for a given gamma. I don't know what it is. I'm just assuming it exists. And all of my bounds rely on whatever procedure you have. So it's true that given one gamma star, there are more than one gamma net possible. But the differences in size between them can be bounded. And to find the minimal one is NP hard. But to find a gamma net is easy. And you can actually bound the difference in sizes between them, the ratio of sizes between them.
But even a very high intuitive level, the algorithm is sampling in the dense regions less often. Your probability of being sampled if you're in a dense region is smaller. Your probability, because Voronoi cells are equal size, so you're uniformly like Voronoi cells.
So this is, so the Voronoi cells are not of equal size. They are based on the points that you sampled. So in that sense, actually, I don't think this is true, because if you do a gamma net on the entire space, you will have Voronoi cells in dense spaces and in sparse spaces, and you will sample the same amount. You will sample the same amount because, at least the way that this is framed, you need to get the same accuracy for each Voronoi cell.
You'll sample one sample in each Voronoi cell? Or no?
A constant number of samples.
So some cells may have more.
Well, here we don't need any more, but if you want
some
to...
cells may have more set points in them. Some Voronoi cells.
Yes, of course.
And those points will be less likely to be sampled.
In terms of the conceptual game here, it looks to me like it is just the hierarchical Gupta should have instead, but you have a fixed cell size rather than being adaptive in every part of the data. Because At the end, that's a nearest neighbor algorithm that decides the size of the cells according to homogeneity based on some samples that estimate homogeneity, which is common to both approaches. And it seems that the main difference is whether gamma is uniform throughout or you allow it to vary in different areas.
So we have different guarantees, right? We don't have any assumption on the distribution, okay? So it is a luckiness guarantee. I'm not saying, of course, not every distribution will gain, but the point is you can just use it, and whatever you get, you get. I mean, that's a luckiness sort of approach. But we can talk about this more offline. So we also have some lower bounds to show that at least some of this is inevitable. Yes. Okay. Okay. So maybe I'll talk about this just a little bit, and I will mention the regression problem also. So just to say that our lower bounds show that you cannot get the same result with a random sampling of the labels. You have to do something active, and that the mg, the number mg that we have in our label complexity, you can't get rid of it. Basically, you have to have it if you want to have this kind of guarantee. Okay, we don't know about the 1/g from the model selection. This we don't know. Maybe it can be improved. So okay, I'll just summarize this part really quickly so that I can also mention the regression part. So basically, we have this algorithm. It's basically a luckiness-based algorithm. You don't need any assumptions, but if you're lucky, then you're going to use less labels than you would have if you just use the passive learner. And we have some lower bounds that show that in some respects this is the best label complexity. In other respects, it's still an open problem. And this is basically this nearest neighbor approach. I do want to spend a few minutes also talking about the regression problem, which is different. So in the regression problem, we're looking at linear regression. We have examples in Euclidean space. We have labels that are real values. We're looking at linear predictors. And we are just looking to minimize the mean squared error of the predictor. We do not assume that there is a predictor that gets 0 error or even that the model is well specified. We just look to minimize the excess loss of our predictor compared to the best predictor that you can get in this distribution. Okay? So we want to do, again, active learning under minimal assumptions. And there are some previous works on active learning for regression, but they all have different assumptions that we're trying to not have in this approach. So the starting point of this algorithm was the following result by Daniel and I for passive learning. So this is a passive learning algorithm for regression that gets bounds that are tighter than standard least squares regression bounds because it basically handles heterogeneous noise. So this is an algorithm where if you have more noise in one direction than in the other, you will actually it will factor into your bounds so that you can get tighter bounds in heterogeneous noise cases. Okay? So this is a passive learning algorithm. And the point for this talk is I want to make it active. So what do I mean by making it active? It means I want to sort of improve the number of labels using an active, using this bound, but improving the number of labels. So the main idea is the following. This bound depends on the distribution. It's of course not surprising, but the idea is we can sort of change the distribution. Okay, so we have a distribution, it's given to us, but we have active learning, which basically means that we can use more unlabeled samples, but we don't want to waste labels. So what we can do is we can take the distribution, we can sample examples from it, but we will only ask for some of the labels. And using rejection sampling, we can use this to sort of simulate a different distribution. Okay, so this is the idea. Now what I want to do is I want to find a distribution that will make this bound as small as possible. Okay? This is a general idea. Let's simulate or emulate a distribution and then run this algorithm, but it will be a different distribution, so we will get a better bound. So we define a weight function over our support, which basically specifies how to reweigh the examples in the space. And it can be emulated using rejection sampling from the distribution, so it doesn't waste any more labels. And we build this distribution so that the loss of on this distribution is the same as the loss on the original distribution. So I can just do regression on this new distribution. Whatever I get is as good for the original distribution. There's no difference. Okay? And the main challenge is how to find such a good weight function, right, a phi. So this is, again, sort of a model selection problem, although it's in a different context. So the thing is, and I'm not showing you all the details here, but this phi, this weight function, actually depends on the true predictor, on the optimal predictor. The optimal phi depends on the optimal predictor. So of course, this is a sort of a bootstrapping problem, but we can get around it by basically, of course, we have to limit phi somewhat because we need some sort of limited capacity class for phi. But then what we do is find an approximation for the predictor. So we find an approximation for the predictor that we're looking for just so that we can then find a good phi, and then we calculate the optimal predictor again based on this phi. So I'll just show sort of the sketch of the algorithm. We have a budget, label budget. We split it into 3 parts. We use the first part to run a regression on the labeled examples from some normalized distribution, and we get some predictor v hat. So this v hat is not so good. It cannot be used as our output, but it can be used to estimate phi. Okay? So the second stage, we're doing another type of sampling from M2 labels and get phi hat, which is our estimate of the weight function. And then finally, we run regression using this new phi hat on the last part of our label budget. So the idea is basically you first do some learning, you use it to improve your weight function, and then you do the actual learning that will get you the predictor that you're looking for. So this is kind of the sketch of the algorithm. And the type of guarantee that we get here is actually similar in the idea to what we got before. So we get the following guarantee. We get that the excess loss that our algorithm gets is almost the same as if we knew the correct phi to use from the beginning. It's almost the same because there is some overhead that comes from having to estimate phi, but this overhead is asymptotically smaller. So we are left with this rate, which is, again, competitive with what you could get if I told you in advance the right phi to use. Okay? So this is row star. This is the optimal convergence rate, and we are basically approaching it using this algorithm. Any questions?
How do you split in budget between M1, M2, and M3 in what is the...
So the way that it's split is M3 is the largest. It basically, when M goes to infinity, M3 will be almost the entire budget, and the other ones are going to be a smaller and smaller fraction of the budget.
So for the phi's, if you could pick the perfect phi's, how would they, so they depend on the squared norm of x and also on the noise level at that, right? So what is the dependence roughly on this? Like, what would you want that to be?
So I don't have it here on the slides, but you can actually, if you know the distribution, you can actually find an analytic expression that tells you what is the best phi. Okay. But of course, we don't know the distribution. That's why we have to estimate it. Another question?
Can you do this for like logistic regression or some other linear models?
I haven't tried, so that's a good question. Okay, so let's just, I'll just summarize. In both of these approaches, what we're showing is we do active learning, we don't have any assumptions on the distribution, we just sort of try to run an algorithm and hope for the best in the sense that whatever it can get, it will get. And if not, then okay, we still got about the same accuracy as the passive learner. So that's a general idea. And so we either get competitive accuracy with less labels, or we get better accuracy with competitive number of labels. And we need to do that, we need to estimate the parameters of the problem interactively, which is what we do. And as I said before, this is a luckiness sort of result. So the actual improvement will depend on the final distribution that we get.
Any more questions? Okay, so let's reconvene at 11:30.